Okay, as atoms in a reactor sample decay with time, we expect the number of remaining isotopes to decrease exponentially. The equation is given by this, where n is the number of isotopes at some point in time t, and n naught is the initial number of isotopes. Okay, so in this case, the initial number of isotopes is here, which is 5.5 times 10 to the 12 isotopes, and at point time t, which is 3 times 10 to 2 seconds, we've got approximately, let's say, around 1.7 times 10 to the 12 isotopes remaining. And lambda here is the decay constant. Okay, as the number of isotopes decreases with time, we expect the activity of the sample to also decrease with time. In fact, they're directly proportional, so we expect the activity to also decrease exponentially. So we can use this equation here. Okay, A is the activity at some point in time t. So we've taken 300 seconds here, but you can use any time and you'll get the corresponding activity. A naught is the initial activity, so in this case we've got 200 becquerels. Okay, and of course lambda is a decay constant. Okay, the half-life of plutonium-239 is 2.4 times 10 to 4 years. That's the half-life. Okay, a sample of plutonium has 4.0 times 10 to 18 atoms of the isotope. Determine how many atoms of the isotope remain after 3.5 times 10 to the 4 years. So that's another point in time there. Here's our initial number of isotopes. I'm going to find n, the number of isotopes after that time there. Okay, we don't have lambda, the decay constant, but we can use ln2 over the half-life. Now I'm going to stay in years here. Okay, I'm going to stay in years. Because that means that I get the decay constant in per years, but it's okay because if this decay constant is in per year and we use our time in years, they'll cancel out. So the exponent will be unitless. Okay, so that's fine. Okay, I'm putting my initial number of isotopes here and then my decay constant and my time. I get the number of atoms left is 1.5 times 10 to the 18 atoms, which makes sense because that's less than what we start off with. Okay, the physicist measures the activity of a rock. The isotope inside the rock is uranium-238, which has a decay constant of 8 times 10 to the minus 18 per second. Determine how long it will take for the activity to reach 20% of the initial activity. I'm going to use this equation here. I don't actually have the activities in becquerels, but I do have the percentages. Okay, so this is going to reach 20%. We're trying to find how long it takes to reach 20%, but I start off at 100%, of course. Okay, so I'm putting these numbers in. We've got the decay constant. Okay, so I'm going to divide it by 100 from both sides. So I'm going to make t the subject ultimately. Okay, and then take natural log. If you take natural log, the exponent comes out basically, and we've got the negative there, so boom, the negative to the other side, and the decay constant as well, and you got a time there. Okay, and then rearranging that, you get 2 times 10 to the 17 seconds, which is approximately 6.4 billion years, which makes sense because uranium has a very long half-life. Okay, sometimes you'll have to use a graph to figure out important information. In this case, we're trying to figure out the decay constant. Okay, so we've got activity against time. So one way to do this, I can just figure out the half-life first and figure out the decay constant from that. The half-life is the time it takes the activity to decrease to half the initial amount. So we can go from 200 to 100. Okay, the time it takes to do that. But equivalently, I could just go from any point to half of that activity, and that will give me the same half-life. Okay, so the time it takes to go from 200 to 100 is around 1.8 times 10 to the 2 seconds. So if I take that half-life and I put it into this equation here, ln2 over that, I get the decay constant of 3.9 times 10 to the minus 3. Another way is actually just use this equation here. Okay, A equals A naught t to the minus lambda t. I can just pick out any set of data. So let me pick out this point here. Okay, as long as it's a suitable point. So here 4 times into 2 seconds, we've got around 40 becquerels. Okay, so 40 becquerels, the initial activity was 200. Okay, and then we've got the time at 4 times into 2 seconds there, and rearranging this, dividing by 200 and then taking natural log and dividing by the time, we get decay constant of 4.0 times 10 to the minus 3, okay, which is roughly the same as what you've got before. The only difference there is because there's going to be some error from reading from the graph.